Now every chapter onwards is only electrostatics. So if you have really understood the electrostatics, every chapter will find just piece of cake. It's just some cosmetic changes here and there. So the entire 12th portion is, you can say, consequence of electrostatics. Let's start. So before we start this chapter or this topic, I would like to know what do you mean by current? Just current. Don't try to connect with electricity, because I have written the electricity word separately. So if I am writing current and electricity, then current must be some generic word, meaning it must explain something more general. So the question to you, all of you, is what you mean by current, or how you take this definition into your brain.
Sir, flow of charge.
I said remove the electricity and think about current as something generic word. You must have heard
Okay.
about the
Okay.
underwater current also. Have you heard this?
Sir, then flow of energy.
Okay. Of course, it's not about energy. What it is about? Streamline flow of particles. Okay. Yeah, of course, that will have some effect as a current. But what exactly, I mean, we define current? So imagine you are in your school and the school all, I mean, the school time period goes, I mean, gets over. Then you see the entire, I mean, crowd, I mean, all students, they start leaving the school gate, and the gate is like an opening through which you can come out. Of course you can cross the boundary also, but that's not legal. So generally you take the gate and you come out of the school. So the school gets open once the class is over, and then what comes out is we can call it students. So this cross section, this is like a cross section, and what is coming out, you can say students. So they are coming from this side of the cross section to this side of cross section. So probably we can count the number of heads crossing the cross section in a unit time. Then we say the gate is having that much of a student current. So current is basically flow of any entity, any physical entity, or any materialistic entity through a given cross section per unit time. So current is essentially a definition meant for some cross section. So until the cross section is not well defined, you won't be able to understand anything. Or you can say current is meaningless to define until we do not mention for which cross section you would like to define it. So what we say is it is flow of anything through a given cross section per unit time. So current we never define for medium. We define for the cross section of the medium which we are considering. Okay. So you must remember, or let me put as a note. Current is not defined for medium, but for the given cross section of a medium. And that will make a lot of sense the moment you study the magnetism, and there is a topic called Ampere's circuital law. So let's say there is a wire carrying some current I. Now, no matter how thin a wire may be, if you cut a small piece of wire and if you zoom it out, what you end up seeing is a cylinder, isn't it? So essentially, a
Yeah.
wire is like a cylinder. And once you look at the cylinder, let me zoom this part separately. I'm just zooming continuously. Then what you see a big cross section, isn't it?
Yeah.
So when you say a current of I ampere is moving through this wire, that is not exactly we are trying to say. We are trying to say the I current is passing through the cross section of the wire, but that is so implicit that the definition has got skewed so far over the time. So no one says the current flowing through the conductor, I mean cross section of conductor, they say current through conductor, and there is a reason for it, which is I would say it's legit to say, because in steady state, no matter which cross section you choose, the current you will calculate to be same. And in that situation, which is the general situation which we come across, in that situation, it is good to say the current through the medium or through the wire. But the reality is, the definition was always for the cross section, not for the wire. And now this will make more sense to you the moment I ask you that if this I current is by some assumption, if it is uniformly spread over the cross section, so this I current is not passing through the wire, it is passing through the entire cross sectional area of the wire. And if I call this radius as R, so this is the area. Through what surface area it is passing? You will say pi r square. Okay. Now, if I draw a small cross section which only extend up to a small r, and if I ask you what is the current through this cross section, the smaller one, so what is the current through this one? Can you guess? Let's say this is the capital line, the net current. If I is the net current, can you tell me the current through this cross section, assuming the uniform spread of the current? What would be the answer?
Capital I divided by pi into capital R square.
Why I will come
I
again?
into sir, sir, I into small r square divided by capital R square.
Correct. So this is called the current through this cross section, and this is also called later on in come to know, this is called the current enclosed by this perimeter, by this loop which I have drawn as a white circle. So until you do not understand the meaning of current, this question or the entire mechanism will look like a very complex topic. So we need to know the definition of current. Current is not for a wire, current is for a cross section of a wire. And in some situation called the steady state condition, because every cross section will count the same amount of current no matter how big or small the cross section is. In that situation, it is you can say okay to say that current through the wire is 1 ampere or 2 ampere or I ampere. So current definition is simple. Current is flow of anything through a given cross section for a time. So it is defined for a cross section. Okay. So it is not defined for the medium, but for the given cross section of a medium. So when you say current, you also say for what cross section. That is very important. Okay. And if we fail to define the cross section, then our definition is incomplete, because as the cross section will grow in value, the current may grow. It depends. Now, in case of semiconductor, what is very interesting that in case of semiconductor, a single cross section can have variety of current. It means current can vary from cross section to cross section, even though the area is same. And why that happens? Because in semiconductor world, you can create a extra electron and hole pair through some mechanism of light, heat, or other methodology, applying potential difference. And because the medium itself is, you can say, non-homogeneous, so it is possible to create a variety of current value in the same cross-sectional area, but at different location. So the behavior of semiconductor is quite difficult to, understand at very first go until we do not know exact biasness or you can see the voltage connection. And therefore, the world of electronics is slightly, not slightly, it's too complex to study compared to the DC circuits of conductors. Anyway, so we'll come to that in future called the semiconductor physics. Although it's not part of JEE syllabus, but still we'll explore that chapter as well. It's good to know because eventually you're going to go into IITs, so or any engineering colleges. So there you have to study the electronics in almost every branch uh, except civil. I think. Yeah. So electronics, electrical, mechanical, civil, except civil. I think, yeah. So in all branches, some part of electronics is there, and computer science is anywhere there. Electronics is anywhere there. Electrical is again of course there. So I hope the definition of current is clear to all of you. Okay. Now, because once we have done with the selection of cross section, then we can define the current. Technically, you need not to worry about these complex definitions. The reason is you're not going to face such situation in JEE preparation. So even though it is a very complex topic, the complexity which you will face is just 1/100th level of difficulty possible. The next thing is we define current in multiple ways. So we have something called types of current. Now, anything. So anything can be charge also. So when charge will flow, what we call is electrical. Now, the current word is so popular that in general, when we talk about current, we talk about the electric current. So I think the context is important because in case of household supply or something, when you say current, you mean the electric current. Of course, if you are some marine engineer, you may talk about the or submarine driver. So you may talk about the underwater current. So current is a, of course, it's a definition which can you can prefix anything and that will become current. So you can say electric current. So electric means current which is related to charge actually. And then you may talk about something which is not electric. You can say underwater current. So it's water which is creating that same assumption of flow through the cross section. So of course, energy current can be also be possible. The light itself is a current actually. So you can say it's a kind of current. Of course, it flows through the space. So you can draw some arbitrary cross section and you can see the current. So when we have a cross section, which is well defined, and when something is passing this, and if it is passing at some rate, so there is maybe some velocity with which it is crossing it. So there are two possibilities. Velocity may be constant, velocity may be variable. And again, there are two possibilities. It may be varying only due to the direction, only due to value, or maybe both. So there are basically few more possibilities. Then what is crossing can be time varying. What is crossing can be directionally varying also. So based on their direction, their magnitude, we have again certain definitions which we would like to define. So I'll call this as a definition of current, types of current based on mathematical definitions. Now, these mathematical definitions are kind of a need-based definition. A need-based means we have come across situation like this, and we wanted to give a single name to the entire event, and so we said it. So we say something called average current. Now, current means flow of something. Then something cannot flow average. I mean, average is what is this is what you are defining. So average current, which we represent by the angle bracket, or if you are not okay with angle, you can just start AVG. So the left one is mostly used by the Russian authors, right is for the British authors. So I oblique IAVG, which means average current. So average means you observe some event for a certain duration. And then you check how much charge, let's say if you're talking about the electric current, of course. So in an interval beginning from T to T plus delta T, the amount of charge which has crossed this cross section must be having some value. So we say the total charge passing over the time interval delta T. The ratio is called average because that's how we define the average for a big interval. And then mathematically, you also define something called instantaneous. So anything which is instantaneous will have a very well-defined definition. It is inspired from the calculus, which we write as limit. When you observe some event for a very small duration, how small, you cannot imagine. It's tending to zero. And when you see how much charge has crossed the cross section in that time, then this entire term we write as dq by dt. So basically dq by dt which we call instantaneous, is the average, but for very small time interval. So when we shrink the time interval to almost zero, then the average becomes the instantaneous, and that is the definition which prevails throughout physics. It is not only meant for current. You can substitute current with any physical quantity, and if you put the word instantaneous, then it is the average for the interval tending to zero. So it could be anything: instantaneous voltage, instantaneous velocity, instantaneous acceleration, instantaneous force, instantaneous momentum, and so on. So you take any physical quantity, and the moment you say word instantaneous, it means it is not the actual instantaneous, it is the average, but for the interval which is so small that we only care about the. Okay, so this is again a confusion. See, we are defining for the area, not per unit area. Okay, so when I'm saying this current is defined for the cross section of the given medium. Okay, so in the direction of flow, I will check the cross section and I will take the entire cross section. So current is defined for the cross section, not per unit area of cross section. Is this clear?
Yes, sir.
Yes, sir.
So current, I am not saying that it is the amount of charge crossing per unit area of cross section of a medium. No, I'm not saying like that. I'm saying for a given cross section, how much charge is crossing per unit time. So I cannot define cross section how big you want to take. It's up to you. You can choose the cross section as big as much you want. Let's say if I create a cross section which is bigger than the dimension. So by creating such cross section, are we creating more charge crossing it, or it is constant? So just because I have increased the cross section, is it making any difference in this case? The answer is no, because we have finite value of medium through which charge is actually flowing. So making a bigger cross section will not impact, because it will only enclose the same charge crossing as the this cross section, isn't it? So among these three cross section, the answer will be decided by the this one. And if you make it even bigger, are you going to get more charge? No.
No.
So now this is called the instantaneous current. And the third is, which is very important for all of us, called the root mean square. So RMS current again is the mathematical definition, and So RMS is generally defined for those cases where the average fails to give you any answer. So let's say if we have a current which varies in such a way that if you try to find the average for the interval in which it will have the equal positive and equal negative area, what will happen is the average will be always zero for this interval up to t. So whenever the average becomes zero, we try to define the RMS. Okay. So what we do is we square the value, and once you square it, what happens? So IRMS, by the name, it's root mean square, so it's a square of the value. First, you square the function. So here current is a function. Take the average, or you can say mean, and then take the root. So why root? Because once you square a function, then dimension will change. So to make the dimension again back to the same value, you take the root. So it is now kind of balanced. So the way of writing is I square. And if it is a time varying function, so we write I square dt as the area under the curve called I square and t curve. Then you divide it by the time interval. So this is the average. And once you're done with the average, you take the root. So this is the RMS definition, and you can extend this definition for any function. If I give you fx, and if I ask you what is the RMS of fx, so you can attach the fx square dx upon dx. So here I have taken dt because it's a t function. If it is x function, I'll take x. If it is some other function, I'll take some other function. So you can generalize the definition. So you can take any function. Let's say if f is a function y equals to f of something psi, I mean something very strange function, then the y RMS will be f of psi square d psi integration d psi, and then take a root. Just to explain the fact that this is a mathematical definition, and this mathematics prevails for any function. It is not meant for current. Current can also have RMS, but RMS is not meant for current. RMS is an idea. It's the root mean square of anything, and you can extend this idea for any mathematical definition which exists in universe. So this was the definition of current, and we need to know certain things here, like types of So before we move further, let me ask you one simple question. What IDT represents? What is the meaning of IDT? When you write IDT, what do you mean mathematically?
The area under the curve.
Yeah, so this is
I
the
versus
area under the curve I versus T, right? Area under IT graph. So generally, when you write y dx, it is the area under the yx graph, right? So whatever you write, let's say if you write f dx, what is the meaning? Area under force and displacement graph. So if you write f dt, area under the force and time graph. So if you write VDT, area under the velocity time graph. If you write ADT, area under the acceleration time graph. If you write ADS, area under the acceleration displacement graph. V square ds, area under the V square and displacement graph. So the mathematical definition of integration is area under the curve. And the first term is called the y coordinate, the dependent one, and the dx, dt, ds, or whatever is the independent variable which we take on the x-axis. So of course the IGT is the area. So the average and the instantaneous. So this graph is representing some I as a function of time t. So how to find the entire area? So you will write I dt. So from the definition of instantaneous current, what we know that I is dq by dt. So dq we can always write as I dt. So if you integrate, what you get? The total charge from given interval, let's say t1 to t2. Then what is the average value? Average is delta q by delta t. Delta q we can replace by the instantaneous variation RET, and delta t we can attach simply dt integration. It is similar way, right? So you can see that every average can be connected with the instantaneous definition. That's simple. Similarly, when you write the RMS, you square the function, then you take the area. So basically I square dt is representing what? I square dt is representing area under which graph?
I square against t.
It is the I square t graph. Okay. So when we have a graph like this from t1 to t2, then how to find the average value of this or area under the graph is this much? Then you divide by dt from, of course, t1 to t2, and then you take the under root. So you call this entire term as RMS. You need to know the meaning of this. What exactly it represents? It represents. Now, in entire current chapter, you will come across an idea of waveform. So waveforms are basically a mathematical shape of the wave, and some of them are really famous, and we should know about. So we have something called a waveform like this. I'll start with the simplest waveform. So if a variation of a current happens then it will repeat itself like this. So we only draw up to one interval. So we call this is I. This is t by 2 and this is t. So what we can see is that, okay, if it is a following some sine curve, so we call it sinusoidal. So the name is sinusoidal waveform. Now for one cycle, cycle means one time period. So one time period is also called cycle. So for each cycle, it is obvious that I dt will be how much? The average, how we define? The average we define the area under the graph upon time interval. So what is the area for one cycle? No need to calculate, you can just check it in the graph. It is 0, right? Because we have
Yeah.
positive area and we have negative area which are equal, so we can say the net area is 0. So the average per cycle is how much? 0. So the moment the average per cycle becomes 0, you do two things. You take the I average, so for per cycle. So now we can also extend I average for half cycle because full is 0. So how to find the I average for half cycle? Imagine, assuming that the equation is written as I naught sine omega t. So let's say this is the variation of I with time. So can you find the average for half cycle? And those who know omega represents time period, so it's omega into t is always 2 pi. Like in one time period, you make one circular motion completely. So one omega into t is 2 pi, but omega is called angular frequency. So omega is 2 pi by. You can also rewrite your expression as. So to find the half cycle average, you will do the integration from where to where? From 0 to t by 2.
Yeah.
I hope you all know the integration. Let me answer. Excuse me. You are only 5 minutes. Okay, what is the answer?
So
Yeah.
it's I naught cos 2 pi by t into t divided by 2 pi by t.
But you have to put the limit also, no? So the limit of
True.
integration is 0 to t by 2.
Okay.
Sure.
Huh.
So 2 I naught by pi.
So the answer is 2 I naught over pi. Yeah, that's correct. For the half cycle, it is 2 I naught over pi. And then Krishna will be what? With the answer. Now you can see that for half cycle we have answer, and that should be the answer because for half cycle we have the area. For full cycle we don't have it. And for RMS, for full cycle, RMS per cycle is how much? Now this is again very important for all of us to know. What is the RMS per cycle? How many of you got this answer? Please raise your hand. Everyone, those who got the answer. I think many got the answer. Athar, you didn't get it. Tanu, you got the answer? So for find the RMS for the entire cycle. So once you find the RMS, it's very interesting. If a function is symmetrical in a way the shape is same above or below, the moment you square it, it will look exactly same. If I is like this, but the moment you make the I square, so you will get a graph something like this. And because of the repetition of the graph, the RMS of the T by 2 or the RMS of the T will be same. Because up to T you have to add only one area, up to up to T by 2. Up to 2 you will add twice the area and time will also come twice. So in a way the average or you can say RMS remains the same. So it is good idea to just find the RMS for the, even I'm asking for per cycle, but you just find for the half cycle, you will get the same answer. The IRMS we can write as I square dt from 0 to T by 2 and then divided by the T by 2 interval. It will give you the same answer as you would have got for I square dt 0 to T 20. So both will give you same answer. I hope this is done. So there are some facts which you must remember that for any sinusoidal curve, so if we have y equals to, let's say, sine theta, the average of sine square theta from 0 to t the per cycle, or the average of cos square theta from 0 to t, both turns out to be half. So the easy way of writing is I equals to I naught sine omega t. So what I'm asking is find the RMS. The way of writing RMS is very simple. So write as I square average and root, which is like I naught square sine square omega t average because I square is constant, root I naught under root of sine square omega t, which is 1 by 2. The answer is. So just remember this answer. Then okay, so you can keep on doing integration at home. The other waveform that we should be aware of, you saw the sinusoidal waveform. The other waveform that we should be aware of, so this is called triangular waveform. In the electrical or electronics lab, you will see something called waveform generator. So we do have a device which generates potential or a voltage in this machine. Generally, we generate the potential, and then you pass the potential through a resistor, which you can design on a whiteboard, or sorry, breadboard, what we call, and you can create the current of this shape. And this kind of shapes are studied. So basically, if you pass this waveform through inductor, if this current will be fed to an inductor, the output will be very interesting. So we will learn later on the EMI chapter. The inductor creates something LDM. It's like differentiating the current, right? So if you differentiate the straight line, what we get is the constant. So what we get is uh, it's like this, like so when we pass the, and that's why the inductor is called differentiator as a machine. So how we implement a differentiation in machine is like this. It's called differentiator. And capacitor act as integrator. So that of course you come to know that uh, how we achieve the first, how we build the first computer. Of course, we have to do a lot of integration and differentiation. And for every differentiation, we use inductor, and for integration, we use capacitor. That happens machine learning. Anyway, don't worry about all these things. So this is called triangular waveform. Again, my question is simple. The I average per cycle is how much, guys?
Zero.
I think I made a mistake. The intervals are not properly written. This is T by 4, this is T by 2, and this is T by 4. This is, so you can see I average is 0, so no need to find I average for per second. So you can find the I average for half cycle life. So it is a straight line. So finding the area under the graph is very easy. So what is the area under the graph? For any straight line, the average is always half of the maximum, right?
Yeah.
Look at this, only this triangle. You get the idea. For this triangle, the average will be only the midpoint because it's a straight line. And for half cycle, it is going to be I naught by 2. You can find by the same, which is area under the graph. So half into base into height. What is the base? E by 2. What is height? Upon the base. It is always I naught by 2. So what is the RMS value? So RMS you can just find for 0 to T by 4. Tell me RMS, everyone, please. So finding the RMS for 0 to T by 4 is same as for the per cycle. I hope this is done. So you can write the equation of this line. So how many lines we have between 0 to T by 0 to T? From 0 to T, how many lines equation we have? Anyone knows?
3.
We have 3 lines. So it's very easy to write equation of each line. So the first segment will belong to a line which passes through the origin. So the I you can write as 3 equations. So when T is from 0 to T by 4, we have one equation, one line equation. From T by 4 to 3T by 4, we have another line equation. So that's part of the different line. And then from 3T by 4 to T, 3T by 4 to T, we have the third line. And it's very easy to write the equation of the set lines. So first line you can see is y equals to mx because passing through origin. And slope is how much? It is I naught by T by 4. So 4 I naught by T is the slope and x is T. So that's first part. For second part, no need to solve. Okay, you can just get from the first answer. You can see slope will invert, so it's minus 4 I naught by T. and T will shift by P by. You can see the center has shifted here. So we just use a shifting of graph relation to get the answer. And the third is pretty easy. The first equation.
Sir, T minus T, capital T.
You simply shift the. Although this is not required for this question, but you should know that how to write the question. If you want to really want to integrate the all interval. So okay. So if you really want to integrate from all the way from 0 to capital T, then you have to break the integration into intervals because the function is changing. But in this case, because we are trying to find the RMS, and RMS is when you square the function. At the moment when you square the function, the bottom will become on the top, and it will look like the same graph everywhere. So what we do is we simply take 1/4, we find the RMS, and that is going to be the answer for each quarter. So how much you got RMS, guys? Tell me. No idea.
Sir, I naught by root 3.
Yes. The IRMS turns out to be I naught by root 3. And again, I expect that you all should get the answer. So how many of you are able to get this answer? Raise your hand. Quickly. Let's do it.
Don't you?
Garv, Anu, Archit. Arga is not able to get the answer.
Sir, I was still doing it.
You?
I was still solving it.
So solve fast. This should not take more than few seconds. Do it fast. Do it fast. You have to integrate, square the function. The function is written here. Square it, substitute it, integrate it, and then and any constant can take it out because you're squaring. So you know. Yes, absolutely.
No,
There
so
we
you
go.
told not to raise
Yeah.
hand if we got that.
You got the answer?
Yeah.
Okay. The third waveform that you should be aware of. It's called the sawtooth waveform. So in sawtooth waveform, what happens? The value of current will grow linearly, and then suddenly will change the direction, shifting the values. It is not perfectly vertical; it's like slightly tilted, but the time to the reverse the direction is so small that we call it almost verse. But always remember that it is all about the time scale which we are trying to observe. So the time period of this graph is much bigger than the switching interval, and therefore change the color. And again, the same thing will happen. It will reverse the direction. And then it will repeat this process. So we have positive, we have negative, then again positive, again negative. So the cycle is, you can check the cycle, it is T by T. And this is I know. So the question is the same thing. I think the average you can see clearly. Average for cycle. So what is the average per cycle, guys? Tell me. The average per cycle is 0 because if you see the area is 0, and because it is similar looking graph than before. So if you look at the quarter, it's a similar graph. So the IRMS will be how much? I dot by root 3. So in fact, for any straight line, for any straight line of no matter what is the slope, the RMS is always I not by root 3 for any straight line. It's a very famous short. The last waveform that you should be aware of, quickly I'll finish. And this is called rectangular wave. Rectangular. And all examples that we saw in these graphs are actually examples of alternating current. So what happens in this case is the value of current will be constant for some interval, but after some time it will flip the direction, but it will maintain the magnitude. So what only happens is here the flipping of direction, but not the variation of magnitude. Current remains same. This is the alternating current with constant magnitude. That's very interesting. It is alternating but with constant magnitude. Understood? So again we have 0, we can set T by 2. So when things are constant, then average will be 0 again. Because we have same positive area, we have same negative area. But RMS will be same. It is going to be I now. Because the values are for anything which is constant, the RMS will be same. Just like I know. So you need to know all this waveform, and these you can expect in AC chapter, alternating current. So now we were defining the mathematical definition of current, and we only define the types of current. So this is the first mathematical definition, and after mathematical definition, we saw all the waveforms. So now we can go to the definition of current based on direction. So based on direction, what we call? So based on direction, we have only two types of current. One is called direct current, in short we call DC. Another is called alternating current. In short we call AC. Now AC itself means alternating current. So when you say AC current, it's like you're saying AC alternating current. AC itself is the complete sentence. Alternating current. Okay, so you know what happens in direct? Direct means direction of flow. Direction of flow through a given cross section remains same. And what will happen in alternating, because the name is alternate, it will alternate the direction of flow. So direction of flow will alternate. That's it. There is no other definition. Now we never talk about the magnitude. Magnitude can be constant, magnitude can be variable. So alternating need not to be variable value. DC need not to be constant value. So I'll show you two examples. If I draw something like this, so how we ensure whether something is reversing the direction or not? We check the sign it. So in one dimension, we check the sign. You can see the entire graph is having location above the x-axis. So it is always positive, right? So this represents a DC current. Represents simply DC. But if you look at this example, this represents AC. Why? You can see if you take the interval, if you take the per cycle, you can see it is changing the direction. So plus means if the flow is right, then minus represents flow is left. That is the meaning of plus minus. So plus and minus always represents the opposite direction of flow of charge. It is clear. The meaning of AC is clear, and this. So this is the DC. This is called fluctuating DC. Of course, it is value is changing. So we call it fluctuating DC. And this is constant AC. So in the EMI chapter, we will come across how to generate this constant AC using the induction process. So it's easy to generate. We actually have the mechanism. Okay. Now the next definition is so based on I can say based on medium property. If a medium is having free charge carrier, I'm not saying electron, I'm saying any medium with free charge carrier, which could be electron, which could be ions, which could be holes and electrons as in semiconductor. Then the current in which the charge is involved is called conduction current. So what is conduction current? A current which is due to charge. Now you will be wondering why I'm saying this. Current means something no charge. I'm saying electric current, of course. So electric current is also possible without charge. That is something strange, but you have to believe it. So conduction is conduction. Conduction current. So what we say is, okay, actual charge flows. And second is very new to you. That's called the displacement current. Current through current through free space that is without charge. And it was discovered by Maxwell actually. And this is the part of a chapter called EM wave. So I'll give you a glimpse of it here. And the more proper usage will be in the EM chapter. Now this is not a, so the conduction current will have two subcategories. So A is called diffusion current. And B is called drift current. Diffusion occurs due to the concentration difference of charge carrier. Due to concentration difference of charge carrier in parts of medium. Let's say if you have a medium in which we have more electron on the left and less on the right, then it will flow automatically. Now, of course, there's nothing like automatic. It's like the asymmetry in the charge distribution will create internal flow, which you don't see. And that internal flow will try to cancel out its own value. So the flow will take place to nullify the internal field or to compensate the internal field, which has developed due to the charge distribution asymmetry. So we call diffusion current. And again, for the present chapter, this in the context of this chapter, what we are studying today, current and electricity, there is no relevance of the diffusion, but it was very much relevant if the chapter is called semiconductor physics. In the world of semiconductor, what really matters is the diffusion current. The drift is having less significance, the diffusion is having a very high significance. In the world of semiconductor, diffusion is very, very important to know. Now, drift is, so diffusion is due to the internal field, and the drift is due to the external applied field. So we need a battery kind of arrangement to create such current. So we say the diffusion is due to internal, and I would say internal, okay, that's fine. Internal electric field. So the flow of charge will take place because of its own flow. I mean, of course, no one is going to push you. You can say these are the self-motivated guys. Okay. The drift is something which you need to push. So we need to apply some external flow. So flow due to applied field. Applied, of course, electric. So in such case, we use a driving force. We use a cell or a battery, whatever, or dynamo. So we use some driving. So circuit is generally driven by some source, and then a driven circuit will have the drift current. So drift means the flow of the charge of the medium as a whole. So when they move together as a bulk, then the motion of the bulk of charge in a medium we call drift. So we'll come to that also. Displacement is quite strange. So let me show you how we can talk about displacement. So I will particularly talk about displacement. So it was B part. It was, so let's talk about displacement in a bit detail. And the way of writing is IT. So now we are familiar with the capacitor, right? So let me draw a large parallel plate capacitor. So let's say it is a part of a circuit which I am not showing you. And if a current is flowing through here, so what current flows through the wire we call conduction current. We write IC. Conduction is the charge. Then Maxwell argued that if the current is the flow, current flow is possible in a closed loop, but this current can only flow up to this plate. So what exactly flows between the plate? Because it's an empty gap. So that was the question raised by Maxwell to himself. So what flows between the gap? Current must be continuous, isn't it? So flow should not stop. But of course, it is the consequence of Ampere law. So when I will teach you the chapter in magnetism, Ampere law, I'll give you a different explanation. But as of now, you can understand that if a current is flowing, suddenly it cannot disappear and reappear in the other side. That was the his logic. So current is coming, it should continue everywhere, even for the gap, but it cannot be similar to gap, I mean similar to medium called conduction, because we have a, this is the space which is devoid of charges. There is no charge in this space, right? So this is called the charge free space. Do you realize this is charge free space? So in a space which is free of charge, charge-free space, can we expect a current which is called conduction? The answer is definitely no. So this current we call displacement current, and the IC in continuity relation must be equal to I. Now this is the way to derive. So we know that at any instant the charge on the plate of a capacitor. So whatever current is coming, it's like the charge is coming towards the plate, and it will get deposited on the plate. So if the charge is Q, the conduction rate is dq by dt, the rate at which charge is getting deposited. So numerically, the displacement must be equal to dq by dt, but the thing is, it should not be expressed in terms of charge, because charge is not the way displacement is created. So what we do is we write the charge in terms of field actually. So we have electric field between the plate, and we know that E we can write as Q by A epsilon naught. That was the formula, right? Sigma by epsilon naught, which is the field between the plates. So the charge we can write as E into A into epsilon naught, but if you look carefully, the E into A is nothing but the flux through this cross section across the plate. This is the electric flux. And therefore, the dq by dt is equal to epsilon naught into d phi e by dt. And this way of writing current is now called displacement current. So, ID is epsilon naught d phi e by dt. So, when charge will keep on depositing over the plate, the flux of electric field between the plate will keep on changing. To the, of course, now this is the flux through the cross section equivalent to the area of the plate. So this flux by default we are calculating for the area of the plate, isn't it? So as the flux will change, now whenever there is a flux change of electric field through space, we say there is a current through that cross section. And now if you know about light, I have discussed this before in web optics lecture. You have happened what in that. Light itself is a oscillating electric and magnetic field, isn't it?
Yeah.
Because light itself is oscillating electric and magnetic field. Then the electric component of light can create electric flux, and that flux can create a displacement current through a cross section. That is quite a possible. It's not at all difficult. So the flux, through the cross section. So if we take a random cross section, so if you take a strip like this, a thin strip, and the field, if I take upward, and of course I'm not just showing the E is here. It is, we have many light there, so E is here. So through this strip we have a flux, and as the light will pass through, you can see the E will vary. So keeping the strip constant, as the light will progress, it will have the variable flux, and so we can say there is a current through this area. So every light, whether it's a white light or any light, any electromagnetic wave, when it passes through the space, it creates a current through some cross section, which you can choose, and that current is called displacement current. So we do have current by virtue of light. Difficult to digest because it's very counterintuitive. So displacement current is the invisible current, and in fact, for that matter, the free space offers some resistance. So there is a resistance of free space because current is finite. Because the speed of light is also finite. So we don't have the infinite of something. So it must, the resistance must be there. So the resistance, it's just good to know. Remember this resistance of free space. We write as under root of mu naught upon epsilon. It's permeability of free space upon permittivity of free space. And come to know permeability in chapter of magnitude. And this value turns out to be roughly 377 ohms actually. So dimensionally it's a resistance match. Dimensionally. Resistance with unit ohm. So the physical quantity cannot be different in dimension. So these will have similar dimension. So the relation. So this is the displacement current, and we are going to make use of this when we derive the speed of light using the Maxwell equation. So we come to that also. So we have to study Maxwell equation. Although we are just supposed to know the formula, but I'll give you a very simple derivation of how the light speed was derived using the Maxwell's equation. So I hope the displacement current is clear to all of you. Not very clear, but you got some idea. It is very counterintuitive. So we have seen the based on medium. Now there is something called based on mechanism of charge generation. Like how charges are created out of nowhere. So we have first called photo electric current. So generally photoelectric current is defined in the context of the experiment in which we have the discharge tube with cathode and anode plate, and we take the cross-sectional area there as the area of the plate itself, and we try to check that how many charges are coming out of that cross-section. And if I draw some hypothetical cross-section very next to the plate surface, then how many charges is ejected by the plate will pass through that cross-section. And once you count that charge per unit time, you call that as photoelectric current at cathode. And similarly, if you try to count that near the anode, it will have a different time because of this speed. While going through the free space, it will accelerate itself. So the rate at which it will receive there is different. So generally, it's a very nice example that you can understand that even if you draw similar cross-section between the cathode to anode, I hope you all are able to visualize the discharge to everyone. Are you guys able to
Yeah.
understand the discharge tube?
Yes.
So in case of discharge tube, can you imagine the plate? It's like circular plate. You can imagine two circular
Yes.
plate, and the area of that plate is the area. So if I draw a cross section next to the plate, so the charge which is ejected by the light will pass through the area, isn't it?
Yes, sir.
And therefore you will measure some current, correct? Now what
Yeah.
happens as it will pass, it will accelerate. So if you take a similar cross section at some distance away, the charge that will cross that cross section will be really quick, isn't it?
Yeah.
So if I take the time interval same for every cross section, we may see a different crossing of charges. Okay. So what we are seeing is that throughout the cross section, beginning from the cathode plate till the anode plate, the current value is not same. Okay. Because of the variation of speed. Understood? But eventually
Yes.
what happens? Eventually what happens? The charge will accumulate between the plate, cathode to anode, and the space will be eventually filled with charges. So when the entire space is consumed by charge, let's call electron, and because of their intrinsic repulsion, they cannot accommodate more and more charge as you progress. So eventually the charge density between the plate will acquire some saturation value. And now what will happen? Any electron which will now ejected by the cathode, the moment that those electrons will enter the medium will throw out a similar number of electron near the cathode plate to maintain the charge density, because they cannot accommodate more than their some natural capacity. So when that happens, then the current through each cross section will be same or different. Now current through each cross section will be same, because whatever charge is entering here, leaving the cathode, the same charge will be received at the anode. It means you can imagine a subsequent flow of charge through the medium at a very high speed, maybe speed of light, and it has reached the other end in no time. In a way, it's not reaching the other end. It is like this, everyone will shift. So when one person will enter, all will shift one step ahead, and the last person will enter the anode. Understood? So in that case, what we define is called the saturation current. So I hope you have studied this in atomic structure in chemistry. What is photoelectric effect? So photoelectric effect means here the photo
Yes.
electrons are generated by the light. So that's why we call photo. Photo means light. So we have photoelectric current. I will not discuss in detail. I mean, of course, these are chapters in themselves. So we have something called thermionic current. Thermionic. In thermionic current, the mechanism will change. We heat the cathode. We don't give light. Rather, we heat the cathode. And because of the heating, it starts ejecting the electrons. So when you eject electron by virtue of heat energy or thermal energy, and if you again consider a cross section area very close to the plate, so whatever will be thrown or ejected by the plate will pass through that cross section. I hope you all are able to visualize that there is a circle kept next to the plate, and every electron leaving the plate is going through the cross section, the circle. Can you visualize the same as I am visualizing?
Yes. Yes.
And because of the, see now you see how powerful is the definition. I said current is defined for cross section, so you can understand that okay, the number of electron leaving the plate is the current through that cross section, isn't it, per unit time? Do you realize this?
Yeah. Yes, sir.
So current there is called thermionic current, and it was the current that was actually measured in the discharge tube, and this was the current that we also measured in the X-ray experiment. This was current which is the typical current in case of cathode ray discharge tube, which was once upon a time we had a television of CRT television. And what is CRT television? Cathode ray tube television. And the cathode ray tube television was based on this thermionic emission. So how we used to generate the electron is, so there was a cathode plate, and of course using the heater. Heater means you just take a coil and you pass a current of high resistance coil. So when the current will pass through the high resistance coil, it will heat it up. So you must have seen heater with a coil with high resistance, and through that we used to eject the electron, and it was the electron which used to hit the screen actually. And the heating of the photosensitive screen by the electron, the scintillation effect was produced, and that is how we used to create the images. So images are like the region of dark and lesser shadow actually. An electron is so small that one visible part of the screen, like the minimum smallest piece of screen which you can possibly understand it's a screen, can create a collision with different amount of electron to give you different shade actually. And by closely monitoring the shade, we used to create the perception of the object image. Okay. Because at the end of the day, in terms of light, every image is the variation of shade from bottom to top. If you look at any image, you can see there is a variation of shade actually. And in the colorful world, the shade can vary not only in terms of intensity, but we can also vary in terms of uh, color also. So imagine that the black and white television of the yesteryear days in 90s, and luckily we were born in that era, so we had a good amount of time spent with those television. And CRT was very close to me because I was so much fascinated by the CRT that whenever the guy who used to come to repair, I was sitting there, and you won't believe the CRT is so powerful. A tester will lit up from centimeters away. Maybe I'm saying more than 10 centimeters. So the electric field that it was developed by the CRT was so powerful that you can activate charge in bodies which are not connected. So in a way, I was looking at the dielectric breakdown at a small scale. Okay, so that's why the kids were not allowed. But anyway, I was that guy, always curious. So that was my childhood CRT, and that's why this thermionic emission is very famous. Now it's obsolete for television, but it is only used for the research purpose and for other discharge tube experiments. So thermionic emission is a concept, and you should be aware of this. I'll explain here. Thermionic emission. So generally what we do is we take a plate, and just behind the plate we put a coil. This is symbolic to represent a plate before this. No, this is fine. I can actually put a coil. You can put some source, and the coil will heat this plate, and upon heating, the plate will start ejecting the thermal, or you can say thermally excited electrons. So if you draw a hypothetical cross section mentally very close to the plate, then definitely we can say all of the electron will come out of this cross section, isn't it? So all of
Yeah.
these
Yeah.
electrons will come out of this. So definitely we have amount of charge crossing this cross section per unit time. So there is a current associated by definition. And this current associated, we can write by a relation called RD equation. So it's a Richardson, Dushman, you can say, or Dustman, whatever. So it looks like one American, other German combination. Anyway, so I we can write here by the okay. He gave the equation that I we can write as a s t square e power minus 5 by kt, and there is a meaning to every term. So let's write a. A is called the RD constant. S is called the surface area of cathode. Surface of cathode plate. Now, of course, this is not a JEE syllabus, but let me tell you, the moment you go to South India, I mean, if you write any entrance test of South, they will have fascination with these questions. So they still ask questions of yesteryear days for some reason. So the test in South, let's say if you go for a VIT Vellore or SRM, in their examination, their test, these questions are still coming, which is not relevant, but they do ask. Or maybe some university exam they do ask. Okay. The T is called the temperature of the plate, the absolute temperature of plate. The phi, I think you all are well aware of, called work function, which is common in case of photoelectric effect. The K here is called Boltzmann constant. Boltzmann, of course, a German. So the name was Ludwig Boltzmann. In fact, this term is called Boltzmann factor actually. So anyway, this is not required. And anything left? I think we are done with every symbol and its meaning. Okay. So photoelectric effect I'm not explaining because it's a separate topic which you have studied in chemistry as well, and hopefully you will get a chance to revise in physics as well. The third emission, I'll just mention here itself, is called field emission or field current, you can say. And the good example for this is called the lightning during the thunderstorm. Lightning. How we write Ligstring? A TING. Lightning. I get confused. Lightning. Is it like this? Or lighting? Tell me, guys, what is the correct way to write?
I think there's no E.
There's no T. Or there's no
E.
E. Yeah, yeah. So Ligstring, lighting.
Sir, NING, lightning.
Lightning. Yeah. Yes. All right. So lightning is what happens. The cloud acquires the charges, and by virtue of the charge, they create a very strong electric field. The field becomes so powerful that it leads to the you can say it tears apart the molecule's electron. In a way, you snatch the electron away from the molecule, and you create the electron and the ions in the atmosphere. And these electrons and ions, when they move through the space, they move so fast, they create a huge amount of energy dissipation, and a part of dissipation converts into light. So you see the current will discharge through the medium, and the collision of ions through the air molecules creates a big sound burst, and you also see some light. So there is a lightning. Okay. So that is example of field current. We do have some other example of field current. We do it intentionally to create a diode called the Zener diode. So in case of Zener diode, we apply the field and we make it very strong to break the depletion region. And by virtue of this breaking, uh, what happens? It creates a large amount of current, and if we use such mechanism to prevent other device from damaging, so that's called the Zener diode. And we called Zener diode as a voltage regulator. So we regulate the voltage across some electronic circuits, because in electronic world things are very sensitive, so a large amount of current cannot be tolerated. So Zener will do something. It will, if something goes really bad, the Zener will break itself. So when the field becomes really strong, the Zener will break itself, and it will, by breaking itself, it will prevent the other device from getting any excessive current. So you can think like it's a small bridge between the something very premium in circuit and some source. So the moment let's say a tank is coming to destroy the city, the bridge is so weak that the moment tank will land on the bridge, it will break. So in a way, the tank will never reach the city to destroy it. So Zener is exactly like this. It is put between the some sensitive part of circuit. So whenever the current or there is some excess of voltage or current, the Zener will break itself down, and by virtue of breaking, it will prevent any extra flow of charges. So that is, of course, we call voltage regulator. Now, semiconductor physics. Okay. The next variety is based on induction. So of course we have a chapter meant for the same called electromagnetic induction. So in induction, what happens? We have a charge, and you vary the magnetic field, and by the virtue of variation of the magnetic field, you apply force on the charge. The force will move the charge, separate it from its own original place, and that is how it will create some charge polarity, and this charge polarity will convert itself into potential difference, and from that potential difference we can drive other circuits. So we called induced current. Okay. So in the name of induced current, we have something called eddy current. So what we have here is called induced current, and the prime example is called eddy current. So we use this idea for multiple purposes, like in applying brakes in train. So in a train, the wheels are made of metal. Okay. So when they move at very high speed, and if you want to stop it near the station, so at every station there is something called traction grid. So what they do, I mean, not they do. I mean, the moment you enter the station, behind the wheels we do have a battery, the charge storage. So they create a artificial magnetic field, which in turn induces the. I mean, it does something. I mean, the mechanism is not quite clear how exactly it is done, but the idea is, by virtue of varying magnetic field, they induce current in the wheel itself, which we call eddy current. And these eddy currents are so powerful, they apply the reverse torque on the wheel. So it will slow down the wheel in no time. Now, if you go by the conventional braking method in which you apply the brake, it will have the wear and tear issue. So it will wear and tear and will produce an enormous heat. But by virtue of the metallic wheels, we use the idea of eddy current, and the eddy current will try to create a reverse torque. And with this reverse torque, we are able to stop the train in less time, because the inertia of train is really tremendous. You can imagine how heavy the train is, and even if a train is moving with 1 meter per second, it is carrying infinite, I mean, tremendous amount of momentum. So inertia is so huge, so stopping is a big difficulty. That's why the high speed trains are having less stoppage, because when you move at such a high speed and you come to rest, imagine the amount of energy you have lost, half mv square. So you don't want to lose that energy again and again. So that's why the Rajdhanis are having less stoppage, and the lesser the stoppage, faster the speed. And you can see those trains which are having a large number of stops, they generally run very slow, I mean, compared to the other. So they keep their average speed 60, 70, or 80, not more than that, because they know that they have to stop again and again and again. So that's whole idea of energy saving. Okay, so induced current, uh, of course, there's a large variety of cases. You can study more about this in chapter itself. Don't worry about it. So right now it is not required, right? Any other current which you can guess? Okay. So one more current is called, I think, which is the part of conduction. I can add here only conduction. What is that? Yeah, conduction current. So when actual charge flows, okay. In diffusion, it is like self-propelled. Drift is you apply a electric field, and there's a third variety which is called convection current. So what is convection current? Actually, you have a medium with charge, and what you are doing is you're neither giving, and there is neither, I mean, any internal electric field, so they're not self-driven. Neither we apply some field to move them. Rather, we take the charge and we run. Simply we run. So with the medium itself is in motion. So far what you have seen is that medium was rest, and relative to the medium, the charge was moving. Now what I'm saying is, what if the medium itself is in motion? So the best example is you take any insulating thread and you put charge on the thread. Now that charge can't move because it's insulator. So when you have an insulating body which are charged, we can set the entire body into motion, and that will in turn will set the charge into motion, and then we can create a hypothetical cross section, and we can define the current through that hypothetical cross section. So when we have a convection, it means the medium is in motion. So this will become too clumsy here. I'll put it here. Convection current. When medium with fixed charge is in motion. Again, for this chapter, this is again not relevant, but the moment we go to the next chapter called magnetism, the most of the tough questions or the challenging question that JEE has ever asked, all are based on the convection current. So convection means you take the current and you run, simply run, okay, or you move, or you make some motion. So I hope we have seen all varieties of current. Of course, I mean there is no end to it. I mean I can just check at the end. Etc. Okay, so the classification of current we are done, and what I'll do is I'll teach you a small piece of convection part, which is important to know. But I'm going to use it mostly in magnetism, and not mostly. I will use exhaustively. So just to give you glimpse of it, let's say glimpse of convection current. And we also talk about the molecular current. So what you need to imagine is every moving charge by virtue of its motion is a source of current. Always remember this. Every. So when I say the glimpse of convection current, what does it mean is, okay, think about a line charge. Let's say we have a line charge. You can think this as a conveyor belt system also. Conveyor belt system. So we know that there, in case of conveyor belt system, we have a belt which is passed over two pulley, a motorized pulley, I would say. And by virtue of the motion of the motorized pulley, the conveyor belts are set into motion. Now imagine you put some charge, a fixed charge over the belt. So as the belt will be in motion, those charges will be in motion, yes or no? Understood? So this question can come in variety of packages. And that's why I said the convection is the most interesting current to actually learn from the point of view of magnetism. So let's say we have a linear charge density lambda. I could have taken sigma on a belt kind of structure, but right now I'm taking a linear charge. Okay. And lambda is the linear charge density. And imagine that this line charge is in subsequent motion with velocity v. Okay. And now what I do is I will create a hypothetical cross section, like big enough to let the charge to cross. Now, no matter how big you take, it will not affect the answer because charge is fixed. So by increasing the cross section area, so can you tell me what is the current through this cross section? Or you can say what kind of current it is able to create. So find the current. So in time dt, how much current will charge will cross? You can find easily. The dq you can calculate, na? In time dt, always when you want to derive something, you can do it for the dt interval. So in time dt, how much charge you believe will cross this cross section? In time dt, what length of the line charge will go on the other side? Tell me. V is the speed given. What do you think? Tell me quickly. In time dt, how much you
Lambda
think? Pardon?
Lambda times V.
You're saying the answer for current?
Yeah.
Yeah, that's correct answer. So lambda V is called the convection current. So whenever we have something moving, so dq connector is lambda V dt, the lambda into length of the wire. In time dt, you will travel V dt. So charge that will cross is lambda V dt. So dq by dt, which we call the convection current, we can write as lambda. I hope this is clear to all of you.
Yes, sir.
And the last for the day, which I'll talk about. So we'll talk about the molecular current. So we call it IM. So imagine if you have a uniformly charged ring, and this ring is set into rotation about its axis of symmetry with constant angular velocity omega, and the charge is q. You could have taken lambda, but I have taken charge. Now, if you imagine again a cross section kind of thing like this, so in one time period, how much charge will cross? Can we say that total charge q will cross in one time period? It's constant here. So the molecular current we write as the total charge upon time period. I hope this is simple. It's q by t, and 1 by time period we can also write as 2 pi by omega. So this we can rewrite as q omega by 2 pi, and 1 by t is called frequency. So sometime you will also see the answer in terms of frequency. Okay. Understood? And
Yeah.
of course, there's no end to it. We will see something more in magnetism. But just to end today's lecture, I'll just end with this question. So if we have, let's say, the Bohr's atom, you know what is Bohr's atom? It's a single electron system, right? Orbiting in various orbits. Okay. So for Bohr's atom, this single electron is capable of creating which current? Molecular current. And if I say this is R, so the molecular current we can imagine here is E omega. The charge is only E, so E omega by 2 pi. E current E omega n. And what is interesting that from the Bohr's quantization postulate, which says that the angular momentum is quantized, which is nh by 2 pi. And from the definition of orbital angular momentum, it is mvr. I hope you remember mvn. And vn we can write as omega n rn square. So you can see the omega n we can replace by nh upon 2 pi mass of electron into Rn square. So molecular current is basically depending on the radius of the orbit in which electron is moving. So as you excite the electron, it will have different radius, we know. And luckily we know that the Rn of the Bohr's orbit is a into n square by z, right? I hope you remember this a naught, which is
Yes.
0.529 angstrom. And the molecular current we can see. My whole goal is to understand the relationship of molecular current with principal quantum number. So with principal quantum number, you can simply write Im is proportional to 1 by Rn square. Rest is constant. So and n, of course, one n is here. And Rn itself is how much? Proportional to n square by z. So molecular current is
Z by N.
I might have made some calculations. You can check and confirm. Yeah, but this is the whole idea. So the molecular current will depend on the principal quantum number, and as you go away, of course, as n will grow, the contribution to the molecular quantum number will decrease. Yes. Yes, this is correct. So with this, we complete the classification of current. The basic, the part one is done. The next part is pretty easy for you because we are going to give you a glimpse of series, parallel, and the other circuit problem we have, which solved already in capacitor. So our primary focus is going to be RC circuit and electrical instrument. So this is the primary focus of this chapter because the circuit analysis we have done a lot in capacitor, and the purpose was we can save time here. But I'll still give you a quick revision of KCL, KVL in the context of current, how to apply it, but will not spend a lot of time there because I have discussed things in capacitor in great detail. And our primary focus will be to go to electrical instrument as soon as possible. So for today, I'll end the lecture here only. I mean, there was purpose to start early, so I have to leave. So bye guys, take care. And this is the like warm-up lecture. You still have time to finish the capacitor. So finish your AC Verma. And once you all are done with AC Verma, try to finish the old JEE problems of capacitor. And once you are done with that also, keep on solving Irodov in bits and pieces. Not required to solve entire problem. But if you just pick a few problems and see whether you are able to solve or not. All right, so your steps are clear. Finish AC Verma, then previous year problems, and then come back to Irodov and solve if you have some time and energy left. Bye and take care.
Bye, sir.
Thank you, sir.
Thank you, sir.